Good evening, madam. Myself, Amrit Kumar, son of Kumarvel. I'm from BELT 2/1. My metric number is B11241041. I'm doing this video for my advanced electrical circuit assignment for the transfer function. Before we go through the question, we start with introduction of the transfer function. A transfer function, usually written as HW, is a mathematical representation of how a circuit responds to different frequencies. It is defined as the ratio of the output to the input in the frequency domain. In this question, we are given the following transfer function, which is HW equals to 200 j omega over j omega plus 2 times with j omega plus 10. So first of all, we have to simplify first the transfer function. To make this function easier to analyze for Bode plotting, we simplify it by factoring the denominator, which means the lower part of the fraction. First, we write the terms in the terms of JW over A plus 1. So JW over A will becomes as JW over 2 plus 1, then times with 2, then JW over 10 plus 1 times with 10. Then we simplify. It looks like 200 JW over JW over 2 plus 1 times with JW over 10 plus 1 times 20. How it becomes 20? Because we will be transferring we will be multiply the 10 and the 20. We will be getting the 20. For the Bode magnetic plot, we start by calculating the initial gain, which is the initial gain is 20 log 10. So 20 log 10, we will be getting 20. So the gain will be the 10 JW over JW2 plus 1. Next, we analyze the slope at low frequencies below 2 radian per second. We have only the zero slope is positive 20 dB decade. At W equals to 2, the first pole causes slope to change the 0 dB decade. Then at W equals to 10, the second pole makes it negative 22 dB per decade. These are the key points on the Bode plot. Let's now we look at a few calculated points for the magnetic plot. The first point is 0.1 equals to 0 dB. Then 0.1 equals to 20 dB. 0.2 equals to 26 dB. Then 0.10 equals to 26 dB. Then lastly 0.100 equals to 6 dB. Still around 6 dB due to the slope pole. These values show how the gain increases and decreases based on the poles and 0. The 0 at origin contributes about positive 90 degree. Each pole contributes negative 45 degree at its break frequency. So total phase shift from 90 degree down to around 0 degree as frequency increases. So based on the calculation we have done over here, I have plotted the graph on the graph paper. So this point 0, 0.1, 0.1, 2, 10 and 100 will be going this way, the lower part. Then the dB stands for here up to 40 dBs. So the 0.01 it's staying here, 0.1, and the dB starts from 0. So the line is starting from here. Then it goes to point number 1, which is 20 dB. So it's showing that the point number 1 is here and the dB is at 20. is crossing the 20 and going upwards to dB26. The point 2 equals to dB26. So here we see the point 2 is dB26, and then point 10 it still maintain the dB26. Then the last part dB100 is decreasing. The slope is around 16 dB, around it's around here 16 dB. As long as we see this, we will conclude that the space over here is 1 decade per second, and the space over here is positive 20 dB. Then the line, the crossing from here to here is JW. That's all, madam. In the conclusion, we learned how to analyze a transfer function, simplify it into a standard form, and sketch its Bode magnetic plot. This is useful in designing and understanding filters, amplifiers, and other frequency sensitive circuits, and so on.
First of all, we're gonna do a first question, which is question D, transfer function. This is the question, which is 50 j omega over j omega plus 4, and also j omega plus 10 power of 2. Okay, so now we're gonna convert this transfer function to standard form to do the magnitude Bode plot graph. Okay, so now we're gonna start convert the transfer function to the standard form. Okay, first of all, okay, so the reason we're gonna put a fraction which is 4 over 4 and also 10 over 10, and especially 10 over 10 with power of 2 is, first we're gonna change the whole number in the equation, which is 4 and 10 to 1, and also we're gonna we divide with 4 divided with 4, and also 10 divided with 10. For example, if at here have a 6, we're gonna change it with 6 per 6, because we're gonna divide with 6, it will change to 1. Same goes here, it will change to 1. Okay, the reason power of 2 is this equation equals to power of 2. So if we need to divide with this equation, we also need change the fraction to power of 2. Okay, now we're gonna divide this fraction with each equation, which is j omega plus 4 with 4 by 4, and as j omega plus 10 power of 2 divided with 10 over 10 power of 2. Okay, if divide means 4 would be 1, and also jw go with 4, same goes here, 10 will be cut, change to 1, so jw omega over 10. So the equation will be like this. Okay, it will change like this. Now we will simplify this equation which we will times with 4 and 10 power of 2, which will be 400, and we will divide with 50, okay, which will be 0.125. so then only we can get a complete standard form for do the graph magnitude Bode plot. Okay, so it will be j omega over 4 plus 1 and 10 plus 1 will be 400, because of we gonna multiply with 10 power of 2. If 10 power of 2 equals to 100. Okay, so next step, as I say, we gonna divide 50 with 400, which gonna be 0.125 j omega, and other will be remain same, which j omega 10 plus 1. So this is the standard form for this transfer function, and also we will use this standard form to do the graph for magnitude Bode plot. Before that, we're gonna identify the basic terms of transfer functions. Okay, first thing, 0.125 we will use for gain. J omega we gonna use with 0 at origin, and this gonna be simple pole, and this also gonna be simple pole, but we also can define as double pole. The reason is we got this equation got power of 2. If they are not power of 2, we can call as a simple pole. If we got a power of 2, it will be double pole. Okay, same goes here. We do not have a power of 2 at these equations, so we can call it as a simple pole. The reason we call a 0 at origin, the numerator we will identify as a 0, and denominator will be identified as a pole. Whatever the, for example, this j omega over 4 plus 1, we keep at numerator, we will call as simple 0. Okay, so that's why we identify this j omega 0 at origin. Okay, after this my teammate will explain about the graph and also how to do the graph. Okay,
Hi, I will explain this Bode magnitude plot, which is show how the gain of a system respond to different frequency. On the x-axis, we have angular frequency measured in radian per second. This axis use a logarithmic scale increase from 1 to 1000. On the y-axis, we have the gain in decibel. Decibel are used to show large change in gain in a compact form. Now, let's look all the plot in the graph. First, from 1 to 5 radian per second, the gain is flat at 20 decibel. This means the system has a constant gain from a low frequencies. it doesn't amplify or reduce these signals too much. Second, from 5 to 10 radian per second, the gain increase at a rate of 20 decibel per decade. This log indicate the presence of a zero in the system, which is increased gain as frequency increase. Third, from 10 to 100 radian per second, the gain become flat again, now at around 40 decibel. This means the effect of the zero is balanced and the system is stable and passes signal in this range well. And the last one, from 100 to 1000 radian per second, the gain drop sharply at negative 40 decibel per decade. This step slope means there are two poles in the system that attenuate high frequency signal. So, in conclusion, this Bode plot likely represents a band pass filter. It allows a specific range of frequency between 10 to 100 radian per second, while blocking frequency that are too low or too high.
Hello everyone, my name is Muhammad Amir Zikri bin Rosnan and my matrix number is B1124105669. So today I will explain about our assigned question H from the advanced electrical circuit assignment. So as you can see, this is the bird plot from question H. So I will explain how it works. So in this region, the magnitude is constantly 40 dB. This indicates that at low frequency, the system has a constant gain. This flat re- this flat response typically suggests the presence of a constant gain term or poles or zeros far away from this frequency range. So at this corner, we call first corner frequency uh, or we know as corner frequency and also known as a break frequency. The change in slope from 0 dB per decade to negative 20 dB per decade at this point indicates the presence of a pole at omega equal to 100 radian per second. A single pole in the denominator of the transfer function causes a negative 20 dB per decade roll off in the magnitude plot. So this is we call mid frequency region. Then the constant slope of negative 20 dB per decade in this region confirm the effects of the pole at omega equal to 100 radian per second. For every decade increase in frequency, the magnitude drops in 20 dB. So this 40 and then should be this is 20 dB. So at the second corner frequency, At the omega equal to 1000 radian per second, the slope changes from negative 20 dB per decade back to 0 dB per decade. This change indicates the presence of a zero at omega equal to 100 radian per second. A single zero in the numerator of the transfer function causes a plus 20 dB per decade, increase the slope, effectively cancelling out the negative 20 dB per decade slope from the earlier pole, resulting in a flat response 0 dB per decade. So at the last line, we call high frequency region, and in this region, the magnitude is gain constant, approximately 20 dB per decade, as it dropped 20 dB per decade from 40 to 20 in the previous section. So this indicates that at high frequency, the system's gain settled to a new constant value. The overall slope is 0 dB per decade, meaning the combined effect of the poles and zeros at high frequency results in no further change in the magnitude roll off. Okay, so in summary, this board plot represents a system of constant gain at low frequency. A pole at at 100 radian per second and a zero at 1000 radian per second. This type of system is correct. This type of system is characteristic of a band pass filter. This type of system is characteristic of a band pass filter, or a system that attenuates low and high frequency less than it attenuates. This type of system is characteristic of a band pass filter, or a system that attenuates low and high frequency less than it attenuates mid-range frequency. But in this case, so for this word plot, it's more like a low pass filter, because from high it go down and then constant again. So that's all from me.